Okay, welcome back to part 2. So I'll talk about deformation in inorganic glasses and metallic glasses. So the important thing to remember is the behavior is going to be strongly temperature dependent. Right? So if the temperature is significantly above the glass transition temperature, you're going to have viscous plastic flow. If the temperature is significantly less than the glass transition, you're going to have a linear elastic material, right? So here's our first case, viscous flow, right? Here's our strain versus time. We give it a load. We have a linearly increasing constant strain rate deformation, and when we remove the load, we don't get any recovery. Right? That's the viscous flow part. The linear elastic part, so this is significantly above Tg. Significantly below Tg, we have a pure elastic response. Our applied load gives us an instantaneous strain, which stays constant until the load is removed, when it instantly recovers. In between, we have our viscoelastic regime, right, where we will have a time-dependent deformation that saturates out, that becomes completely recoverable, right? And our total deformation, right, as a function of temperature we can think of it as the contribution from these three components: the elastic, the viscoelastic, and the viscous flow. And the deformation mode that's going to dominate is going to depend on the temperature. Okay. So the elastic portion is due to stretching and distortion of the bonds in the glass network. Remember, SiO2 forms covalent tetrahedra, and elastically we're stretching or distorting those bonds. Right? So the viscous portion is due to permanent relative displacements of the SiO2 tetrahedra, meaning breaking and reforming bonds. And the viscoelastic portion is due to conformal distortions of the network. Rotations and changes, stress-driven rotations and other types of shifts in the network that have a time-dependent nature and are recoverable. Okay? So anything that you do to the network, the SiO2 network, is going to alter the mechanical behavior. Right? So here we have pure silica, and if we make a soda lime glass, meaning adding some Na2O, sodium oxide, and calcium oxide, right? It alters the glass structure, and we have a lower viscosity. Now the sodium and calcium don't actually jump into the silica tetrahedron. They live in the rings. But because they have to have charge balance, the ions, right? These are ions. After charge balance has to be maintained, it basically breaks the network, right? So that all the tetrahedra are not all joined together in the same way, right? So you can imagine this giving you greater free volume and reduced viscosity. different additions have different effects, right? Soda lime glass or window glass, borosilicate glass, which is a tempering glass, right? Borosilicate glass is what Pyrex used to be made of. Okay, and just notation. There's some notation here from the glass community. So the melting point is obvious, right? Above this, we're a liquid. The working point of glass is the highest temperature that you can have where the viscosity is not so low that it flows uncontrollably, right? That you can still work it and have it retain its shape long enough for you to do what you need to do. The softening point is the lowest temperature where you could work the glass, where below that it's too stiff to effectively manage. Right, and these are kind of just arbitrary definitions. The annealing point is where you would hold it to reduce overall free volume, right, and reduce defects in the glass. And the strain point is the point where below which it effectively acts like a linear elastic solid, right? You'll have very, very limited flow. Okay. Metallic glasses, on the other hand, are exceptionally strong materials. They have very high yield strengths. These are some older glasses. There's newer glasses based on copper zirconium system. They usually have beryllium and titanium and aluminum in them. Zircaloy is the common one, right? But it has very high yield strengths, right? Here you can see these are 2 to 3 GPa, right? Elastically quite stiff, like other metals. What's not shown here is they have exceptionally high elastic limits. You can get elastic strains on the order of 2%. Right? Compare that to a crystalline metal where you have an elastic limit of 0.2%. So you can get an order of magnitude more elastic stretch out of them. Incredibly high yield strengths, and very low tensile strength to Young's modulus ratios. Okay. The problem with metallic glasses, like other glasses, is they are incredibly brittle. You don't have a lot of tensile ductility out of them. And Ashby popularized these deformation maps for metallic glasses. So basically down here we have homogeneous flow, where we're in this elastic or viscoelastic and viscous regime. So if our stress is very low or our temperature is high, we can get homogeneous flow, right? But these are very low stresses. At any reasonable stress or temperature composition, the material will deform by shear banding. The flow becomes very localized, right? And we're in a non-Newtonian regime, right? So our viscosity is going to depend both on our temperature and our strain rate and our free volume. And what happens with, oh, I got text. Text messages. Sorry about that. Our free volume is a function of both the temperature, or viscosity is a function of the temperature, our strain rate, and our free volume. And what happens in the shear band nucleation is local free volume fluctuations can give a small region of higher strain rate, and the shear band can nucleate. Right? And there's a kind of still a lot of debate about how exactly these shear bands generate and propagate. But nucleating a shear band is difficult, but propagating them is easy. And the shear band generates frictional heat, and this happens so quickly you can kind of think about it as adiabatic. So you have local heating within which is going to greatly reduce the viscosity within the shear band. So once the shear band starts, it's a lot easier to keep deforming along that shear band than it is to nucleate a new shear band. So basically, in a metallic glass, once you start a shear band, it's just gonna propagate all the way through, and you're going to fail locally right on it. And so that's why you have no real significant ductility in a homogeneous glass. This is some simulations in metallic glasses where they have a local free volume distribution in this model. I forget, I accidentally cut out the reference, but you can see how the shear bands form, right? And notice they form at 45 degrees, which is going to be roughly the direction of the highest shear stress, right? If we're giving this a tensile or compressive load. Right? And experimentally, we can see here if we're doing compression, these are small pillars, a couple millimeters across. If you compress these, you see you get these shear bands and catastrophic failure in the sample. Right, and these are what the shear bands look like for indentation, a Vickers type indentation test, and in a bending test. So once these shear bands, once you trigger a shear band in a metallic glass, there's not a whole lot left to do. A current area of research that I'm interested in is deformation in metallic glass composites, where you have crystalline regions and amorphous regions. So you get the high strength from the amorphous region, but the crystalline region deforms easier plastically and allows you to get some more ductility. The crystals basically block the shear bands from propagating all the way through, and they diffuse the intense shear within the shear band by activating multiple slip within the crystalline regions. And by doing that, you can get some significant ductility out of metallic glass systems. Okay, next part is polymers, deformation in polymers, and then we'll